people don't realize, but from the very beginning, the only lifeboat available at any time for any crew member for 20 years, 2001 until last year, was the Soyuz. The ultimate, most noble function, which is to save people, has been only with the Soyuz for 20 years.
I'm really honored and thank you for taking the time. I'm sure that you have lots of things happening in Dubai and schedule. And...
No, there are things that are strict. It's the timing of the session where I am involved. But besides, it's just we can customize the way we want.
Okay. First of all, I would like to have a quick introduction about yourself. I read a lot about you.
Oh.
And I was fascinated by the breadth and depth of the things that you had to go through. You had degrees in mathematics, astronautics, you're a flight test engineer. You were picked to be an astronaut at the age of 26. This means that you have like 33 years of astronaut experience.
A record. It might be a record of duration of employment as an active astronaut, because I am one of the rare ESA who stayed active, like Claude Nicoli, I think is the only other one, until the age of retirement, which is 60 at ESA. So that makes 33. It's long.
Long way, especially with all the other things that you had to go through. You were responsible, you were charging man-machine interface. You did
because at NASA we try to put astronauts in between training and missions in some position in the program where we can bring our expertise. They call that job assignment. And my first job assignment was robotics, because NASA realized I had a good cabling in my brain to think robotics and 6 degrees of freedom. Because when you fly a robotic arm, you have to think not only position, but orientation. That makes 6 parameters to control at the same time. And then they realized, and I told the chief of the office, I am very keen on man-machine interface, because any machine is an augmentation of the human being. And I like when it is natural. And by the way, now you don't have to read the user's guide. If you make some mistake, there is no consequences. It tells you make it. So this is quite easy. But when there is safety engaged, when there is a complex technical system involved, you need to understand what's behind just the buttons. And that requires more thinking to make the link between the machine and the humans the more efficient. Because what is the astronaut job? People don't realize, because people don't know. That's why people are asking. There is an astronaut panel on Friday. And the question is, can everybody go to space? And the question is stated in thinking that can anybody replace the astronaut of today, which is a wrong question. Can everybody go to space? Yes. Can everybody work in space? No. And the selection process, the training, is not to make us able to live in space. Not at all. I mean, 85%, 90% is to prepare us for the work. And because we need to fly, to control robots, to do some tasks like EVA that are very physically demanding. We need to be sure we have a good vision, we are skilled with our hands, we have a good heart. And this is not needed just to live in space, because living is to sleep, to eat, to wash yourself, to go to the bathroom, and that's it. And recognize the three emergencies in case you have to put back your suit on. And this, almost everybody here can do that. I mean, being an astronaut, the tough part of being an astronaut is of course to have the boldness to sit on top of a rocket, and that's common also for tourists. That's the same. I mean, a billionaire who is ready to sit on top of a rocket is bold. I mean, he's more than a tourist. He has a kind of adventure, a taste for adventure and exploration to do that. But beside this, you cannot compare, or pilots will never, of an airline, they will never fear that the passenger one day takes their job. So the question is useless. I mean, to come back to what I wanted to say, to be an astronaut consists of being an operator of complex machines in extreme, hostile, confined, isolated environment. That's it. Of course, we are paid to communicate, but the complex machines are the spaceship, the spacesuit, the robotic arms, all kind of scientific instruments. We are not doing research. When you hear astronauts are doing research on board the ISS, it's a shortcut. It's not a proper way to say what we are doing. We are operating scientific instruments, but we are not the one doing the research, analyzing the data and publishing in magazines. These are scientists on the ground. We are operating the machines for them. The DNA sequencer, the microscope, the glove box for biological. We are just the operators. Extreme because temperature, pressure, hostile because of the debris and the radiation, confined because we are in a small volume, and isolated because we are away from any help accessible, readily accessible. Anyway, it was a bit long.
Actually, no, it wasn't, because you just gave me lots of questions to ask you. So first of all, you mentioned that who can go to space, and I agree
almost
with
everybody.
You, everybody, but who can?
You must have at least a relatively good cardiovascular system, because you are subject to some physical events that are not painful, not as difficult as jogging, but that can provide stress for which your heart might have a peak. But if you are not cardiac, if you don't have, stents or artificial valves, or then you can easily, no problem at all.
But from a technical aspect, I'm curious as to if right now a group of astronauts are on the International Space Station, does everyone know how to do everything, or do they have to, just in case there has been...
No.
This is why I'm interested in how much does someone have to know about all the operations that you're talking about, and the processes and logistics and emergencies, to be able to are they complementing each other, or everyone is at the same level just in case?
Everyone has a basic knowledge of everything. But now for a given mission, we will specialize in order to have time to train. Otherwise, it would take years to train everybody to the same expertise level. So if you know you're not going to do a spacewalk, you will not train to the expertise level for spacewalk, but you will do some training to understand, because you might have to do some work during a spacewalk from inside, called the IV, intravehicular activity. Yeah. It's a name we give to the activity that supports from inside the work that's done outside. So there is a grid. You can find a grid where we tell within a crew what is the minimum requested with an expertise level for this. And for each system, each kind of activity, rendezvous, spacewalk, robotics, you have at least 2 people trained with the expertise level. But not everybody needs to get that. You have expert, you have, there are 3 levels, kind of basic, good knowledge, and experts. I don't remember the exact terminology. So not everybody has the same level of training to the expertise level for everything. But everybody knows a minimum of everything.
Because this will make me transition to my other question. So you had 3 space missions, one in 1994, 1999, 97 and 99. And the third one was specific for a mission for the Hubble space mission, which was the focus of your book.
Yes, rescue mission, yes.
So my question is that having a degree in mathematics and all your experience in astronautics and a flight test engineer, something like a Hubble telescope, is it something specific that you had to prepare for, or your technical skills and being able to maneuver really 60 degrees of a robotic arm was helpful? Like, how did you...
The training for such a mission can take any astronaut, a professional astronaut, from whatever background, and get that person to the level needed. So not everybody at NASA was qualified for flying the robotic arm. For some reason, some astronauts who went through the selection process, during which we test motor skills, don't manage to pass the qualification. But it's rare. It's a small proportion, and it's surprising. It happens that for me, since my childhood, independently of my studies, my brain is like this. I can mentally visualize in 3-dimension things. That's why I like puzzles. I flew the Rubik's Cube 3 times on my spaceflight because I like, puzzles and 3D. And, when I was a kid, I was drawing my bedroom upside down. So I was looking around and trying to draw such that once turn 180, I would compare to see if I was doing the mental math correctly to revert the size of the table, the chair, the bed, But astronauts were initially selected among test pilots because that's the closest profession to the astronaut profession. But with the shuttle program, NASA started opening to other type of operators, airline pilot, helicopter pilot, scuba diver, professional scuba diver, Navy SEAL, submarine officer, a woman taking off in a few days, she's a submarine officer. A lot of engineering, we select now in the group of astronauts, you have engineers, and you have even a wider range of astronauts coming from scientific professions, astrophysicists, nuclear physicists, heart surgeon, chemist, vet, volcanologist, oceanographers. Wherever you come from in terms of profession, once you are selected, you're supposed to be able to train for anything, for any mission. Of course, for me, for that particular mission, that was decided very late, with only 6 months of training instead of the minimum 1 year training for any space shuttle mission. It was a mission that NASA decided to add late, just because the Hubble was starting losing too many gyroscopes. So NASA, the chief of the office, called me and said, normally it's not your turn to fly again because there is a rotation. But we need your skill for that mission because you might have to capture a telescope that will not be friendly. Because on all other missions, it was able to control its attitude. So it was just steady, upright when the space shuttle was closing in. So for the guy flying the robotic arm, it's easy. It's like grabbing a fixed object. But when you have to do tracking and capture, it needs to be easy you need to take an operator that can do that without needing too much training to get to the proper level. And NASA told me we had only 3 candidates within the group that have appropriate skills for flying the robotic arm. Nancy Curry, but she had just flown a space mission. Jane Davis, but she had already accepted a management job that normally doesn't allow her to come back. Otherwise, it's unfair for the others, because when you're an astronaut at NASA, you get a certain grade in terms of salary and hierarchy level. And if you want to get a management job where you are paid more, you accept that you leave the active core. Not only because it will be a full-time job, so you will not be able to maintain your proficiency by going to the simulator regularly, but because if you can do that and come back, it's not fair for the others. And she had taken a job at the Marshall Space Flight Center full-time. So he told me, yeah, now we have you because we know you can do it. And it was fun. And you know, I did even tracking and capture with degraded mode where the stick don't work. You have to select each joint one by one, like this one do this, then this one do this, then this one do this. And you have to know which joint in which sequence with which amplitude to mimic what you would like to do naturally to grab the telescope. It was fun. I liked it. It was like a game, like a video game.
And was it because the technology probably was a bit older than what we currently have in terms of the dexterity of the arm?
The arm we have on board the space station has the same degraded mode for which they train, manual mode. But most of the payload are equipped now with special targets that can be recognized by a pattern recognition system. NASA tried and tested with Canada a lot of concept for recognizing that where is the target and what is the position and the orientation of the target. So the arm does a lot on board the space station in automatic mode because it's going from a fixed point to a fixed point. You take a payload that is attached somewhere, you know the coordinates, to take it to another place for which you know the coordinates. So there is no need to match an imperfectly known position and attitude of something. Like when you capture a satellite, whether it is friendly or not, it is not fixed relative to you. So if the satellite is equipped with those target white with a big black dot or square that can be recognized and flown automatically, you have to fly manually to the target. But that is quite easy to program, to write a software, an algorithm that allow a good recognition pattern that has a good visual AI embedded in the software to do it. So now the robotic arm of the space station is flown a lot in auto mode or flown from the ground, because for most tasks we don't need the capability for human to adapt real time to continuous non-perfectly known position attitude of what you want to grab. So today the robotic arm of the space station still has the same basic software as a spatial arm. There is some technological improvement, but when an astronaut is in charge of flying manually, it's still the same basics, the same fundamental things you have to know and practice.
Okay. You just gave me a follow-up question. So I was reading a book called the Checklist Manifesto, and it was written by a surgeon, but what he discovered is that he was identifying two types of errors. He was identifying the errors of ignorance, just because some people would not have the full information when they're doing a task, and then there is the errors or the mistakes of inaptitude. Is that a
either lack of competency or not
lack of competency per se, but for example, missing to wash your hands before an operation, forgetting something like this.
Skipping a step.
Yes. Yeah. So what he was saying is that in different scenarios, such as a surgery or operation or even a flight, like a pilot, like Airbus, they have devised a form of checklist.
Yeah.
And he was saying that there is a specific condition for this checklist to work. If something went wrong, the pilot would go over the checklist to make sure that he's doing the right thing in a moment where he doesn't want to think so much. At the same time, even if he's very competent, he doesn't miss because of anxiety. Is there something similar for
Yes.
the ISS?
Yes, it's similar. In fact, when we train, we have checklists, and NASA gives us a book that's called, what's the name of this book? The exact name? It's a book that has a rationale for each step written in the checklist, so that we understand why it is written this way in this order. So we have a possibility, we have the capability, thanks to this, it's called Procedures Handbook. Not procedures, just procedure, it's the Procedures Handbook. That's a book that describes the rationale behind the checklist. And that allows us, at least once in our career, to have, we know we have understood. We don't remember sometimes all the rationale, but at least we know we have understood once the rationale, and we know why we have to do this way. But for the key or critical task, we have in mind what is behind each step. And some astronauts think that they understand enough the rationale for no need for details. And I know some other astronauts during training, they ask, please add this and add this. They want, like, in case they wouldn't be able to think like a monkey, they want to make sure they will not forget something. So some astronauts are asking to double the checklist because they ask all details. And some others, they don't like when there is too many, when many steps there are so obvious, common sense. It complexifies visually the checklist, while just a half a page would suffice to do the job. But the average astronaut, I mean, so sometimes the people in charge of the checklist, the instructors, they disagree. They say, no, we prefer not to put this because it will more disturb you than make you being performant. And sometimes when you want to remove things, they say, yes, we can, or no, we should not. It's because we think this is important. But it is very similar. And when you practice a checklist, you should not practice blindly, because there are combined situations that might lead to failure if you follow strictly, honestly, the checklist. Mm-hmm. So we are trained to follow a checklist with some intelligence. We develop an intelligence to understand where we can deviate for the good or not for the good. So we are formatted as problem solver. And the checklist covers up to any combination of two malfunctions, but not beyond. It will be too big. So when we have one malfunction plus another one coming in the next minute, it's covered. You could almost do blindly. But as soon as we are beyond two, the first thing we must ask ourselves, is that third failure that just came up, is it so critical that we should jump to that one and leave aside the process we were in to solve the two first, for which we have not finished yet the procedures? If yes, we do it. If not, we continue to process to the end the first and second before we treat the third one. And this is where the common people cannot be astronaut. If you consider astronaut is a profession, a space flight participant is somebody who wants to experience space and live in space, but not in charge of flying, repairing, flying the whole. This is what makes a difference. We are trained to solve problems. We are formatted as problem solvers. You will have problems, but you will be able to solve them. And the instructors are not allowed to give us scenario without solution, but they can be very nasty. So sometimes we have air leak, propulsion leak, fire, short circuit, the control stick which doesn't work. And we have to find a solution. And we are very good. We are Superman when we are close to launch, because we have developed this mentality as a crew. And to the point that sometimes, hey, yes, one more malfunction, we will show them we are very good. Or sometimes, yes, we failed this, they failed this fuel cell. What is the worst thing that can happen to us now? I bet they will fail now the IMU number 3. And up, so we are prepared. And the checklist becomes, basically, we don't follow necessarily strictly blindly, but we respect the spirit of the checklist. And if we deviate, we do it always with a good understanding of why we deviate. We don't skip a line just because we want to go quicker and say, okay, well, let's skip some. This is not important. Let's skip so to make sure we get quicker to the end of the check. No, we don't do like this.
Thank you for sharing. I just have also a question that I was interested in. Where does the nickname Billy Bob came from?
My first crew had a hard time to pronounce my first name correctly, so they asked me if I had a nickname at home. And I have a twin brother with whom we call each other Billy since we are like 8 or 9 years old. We watched the movie Billy's a Kid when we were like 9, 10. And even now, we are 63 years old now, and he calls me, I call him Billy when we call him. I said, Billy, that's good, because when they try to read my name correctly, Jean, which is a female, is Jean. It's a woman first name in the US, in America.
Yes.
Jean. So they say Jean-François, although I is after O and not before. Or Jean-Françoise, when they try to remember their French class at school. So they started calling me Billy, and then after 2 weeks, I think the husband of Hélène Ochoa was on my crew, he said to the others, Billy doesn't sound right, just stand alone by itself. In Texas, we usually have the nickname of the first name and the nickname of the middle name put together. So they decided, well, it could have been Billy Joe, but so they added Bob. So since that time, I am known as Billy Bob more than as Jean-François among the American astronauts. Yeah.
That's cool. So you were in charge of man-machine interface, and you were developing the cockpit for the aircraft. I come from the
spacecraft. For the space station, which is actually the cockpit. It's a network of laptops. There is not a cockpit per se like in an aircraft. It's a set of laptops, and on the laptop you can, for the system laptops, like this, you can call the page that mimics the modules or that mimics the systems graphically, and you click on icons to call the pop-up to turn on a pump, or to switch a valve, or to change temperature, or to manage malfunctions, to reroute when you have to go to the backup systems. And Bill Shepard, the commander of the first crew of ISS, the first increment in November 2001, was preparing for that, and he knew I was keen on ideograms and icons. So he asked me to run the team developing the interface, and I was a co-chair with the former flight director of the IDAX, International Display and Graphics Standards, which would be accepted, which would apply to the Japanese, the Canadian, and the Europeans. So I've been chairing this for quite several years, and I went to Japan, Canada to explain why we decided this icon, for example, for the survival mode.
Yeah, you just gave me two interesting questions. I don't know which one to go for. So you were in charge of the physical aspect and the software interface?
Alors, I was not, within the office, those who are not training or in flight, they have jobs that are structured within a team, within the office, we have branches: the space station branch, the space shuttle branch, the EVA branch, and within the space shuttle branch that was directed by Anna Fisher, former astronaut. I was in charge of software qualification and man-machine interface. I had like a sub-branch, and I had maybe in my branch 5-6 contractors, engineers, and few astronauts. And so I was not myself going into testing the software, but I was managing the team doing that, going regularly to the Cape and testing the actual flight software, and they were reporting to me, so I could report to the branch to have a report weekly, monthly. But I was more involved with my person with the team working on developing the displays in coordination with those writing the procedures. Because one key element, for example, whatever word is used in the checklist should be the one used on the label of the switch. And there were so many differences. There were so many discrepancies between those writing the checklist and those developing the displays, because they thought that astronaut would understand even if it's not the same term. But it's like verify is not the same as check. And sometimes they were. Checking is check that the switch, main bay is on position 1. And that means if it is not, that is not normal, and you have to ask the ground or go into the checklist why it is not in the right position. When you say verify, that means it should be there, if not, make it so. You see, it's a big difference. Check is, you see if it is like you expect, but if not, you don't make it like you expect. You first understand why it is not where you expect. But the term verify is formally used in the checklist now for make it so if it is not like this. So it's a big difference, and a lot of things like this were mixed. It's like the arm fire concept. When you have a critical action to take, you open a valve, which is critical, which opens to vacuum. Or before you do it, you have to allow that switch to work. So to make sure one wrong switch throw will not screw up the... And all those kind of things, they talk to me, because it's something I feel wired for these kind of questions. And so I was managing a team, one doing software for the space station. I was not directly involved. For the space shuttle, I was directly involved. I was in the simulator on the commander seat, flying the rendezvous, the re-entry, the landing, and I had to succeed the landing, because if I don't succeed the landing because I'm a poor pilot at the landing, they cannot qualify the software. The software must run until the space shuttle stop on the runway in the simulator. It was not a simulator, it was an actual orbiter vehicle 99, called SAIL, Shuttle Avionic Integration Lab. It's like a real one, a real software, real computers, real cockpit. Some actuators are real, but it's an iron mock-up. You understand what I mean by iron bird? I mean, it doesn't fly, but it mimics all the real systems.
It sounds like, because I have a background in space architecture, lots of this is human-centered in nature. Because you are taking into account the position of anyone who's going to be in that cockpit,
yes,
and make sure that what can go wrong that we can take.
Yes, I should always have in mind to not access something that is acceptable to me just because I'm very good at that. I have to think about any astronaut, including those who are not expert in that field. It's like a test pilot should do the same. And also, you know the Cooper-Harper scale? It's a scale for a given task. Is it easy, medium difficult, or hard, with effort to compensate, or not with so much? You can rank the difficulty to perform a task, and depending on the ranking, you need to modify or not, depending on the time left or the budget, or unacceptable or totally acceptable. So we use this a lot to rate the quality of the controls and commands.
May I ask you a question?
Yeah.
So about the interface. So I know that on the International Space Station, a colleague of mine had her thesis about the different software and interfaces used across the International Space Station. And what she discovered is that there are many of them and not all the same. So you have to be able to understand and work with different interfaces
because
order to...
NASA initially imposed to all partners one software to write all the laptop displays. So Europe, Japan, and Canada and bought thousands of licenses for all those, And NASA decided on its own one day, because it was too difficult, to go to C++, to another language. And the Russians went with a variation because the license they couldn't buy the license that was identical to the one had the. So it started making slightly different operating system. It was under Unix initially. I don't remember the name exactly. Unix, it's a former. And so now they are still good commonality, but the software behind running the way the displays work and how the command and controls work is slightly different. So it's painful for the controllers, for the designers, but it's more or less transparent for the crew.
Okay. Because then all the astronauts from Japan, Europe, and United States, Canada, they all have to learn everybody's...
Yes, but at least the icons are the same.
Okay.
They don't look necessarily exactly the same style, but you recognize this is a thermometer, or this is a valve, or this is a transducer, or electrical, converter. So at least there is commonality of the concept of the icons. But we haven't reached the standards, the initial fully common standards across the station that we aim for at the beginning. It's the same for the units. NASA directed all the partners, let's go matrix. It was easy for us. It was easy for the Russians who came later, because both Europe and the Russians, we were already matrix in our industry. But Canada and Japan had to make an effort for their industry to go matrix, and they went matrix. The robotic arm of the space shuttle was in inches, and but the robotic arm for the space station is in matrix. But the US industry didn't succeed. It's a pity. That's why all the American equipment on board the space station are in English units. They have, so there is no more Fahrenheit. That's good. It's all Celsius. But you have inches, feet, pound per square inch for the pressure. And NASA recognized that the US space industry failed. NASA failed helping the space industry to convert into matrix. So on board, we have two toolbox. The toolbox with wrenches in millimeter, and the toolbox with wrenches and bolts in 16 of an inch. And, but it works. It's like for the language, the universal language was supposed to be English. And when the Russian arrived, they signed, okay, English as the operational language. And when the first Americans started training in Star City, the lectures were in Russian. And they say, hey, you signed English. They say, yes, English as an operational language in orbit. But if you want to learn how our system works, our instructors, they speak only Russians. And that's why today, all astronauts of all partners flying to ISS speak as a minimum American, English, and Russian.
Do you feel like this will change?
It's not necessary. For the gateway, the Russians will not be part of the gateway, unfortunately. So English will become the only language for the gateway.
How come they are not part of the gateway?
I think it's politics. I cannot judge exactly, but I have the feeling, I understood that NASA is not treating the Russian equally like they do for ISS when it's a question of the gateway. And the Russians wanted NASA to make some move to accept that some of the standards will be the Russian ones, like for electricity or for water. And the NASA gateway management wanted to stick to their units, their standards, and their management of the program. You know, when the Russians arrived, they were treated equally because they had the Soyuz. You know, when people say that since we stopped the space shuttle, NASA needed to depend exclusively on the Soyuz for return and for transport. In fact, people don't realize, but from the very beginning, the only lifeboat available at any time for any crew member for 20 years, 2001 until last year, was the Soyuz. The ultimate, most noble function, which is to save people, has been only with the Soyuz for 20 years. So that's probably why NASA had to accept, to treat the Russians equally. But in the gateway, if the Russians had been in the gateway, they would have been treated like JAXA, Canada, ESA, like partners, but below their leadership. And the Russians didn't find that fair and acceptable for them. That's why they announced they will go with the Chinese.
It's unfortunate.
But I don't know if they will go because they don't have the budget. But this is politics, so I'm not able to judge really, but it's a pity. We feel Astronaut, it's a pity.
Because I'm sure that you've established connections and
friendships
and networks and family for whenever you're there together.
Yeah. Even program managers, at the program management level, there is a big respect across partners, including Russians, and they get along well. But, it depends also directly on the person in charge. You have this manager or this one, or you have this agency lead or this one, or you have this president of your country or this one, and one person can make the difference. But at the time the Russians joined the space station, it was the ideal cooperation in space with equal treatment, respect. NASA decided to stop developing their reboost system because the Russian side has a propulsion system. There is no propulsion system on the US side until they docked with the Crew Dragon. The Russians decided not to take the big gyroscope on board because NASA had already planned them for their segment to rotate the station, without consuming. So there was a good cross-confidence where each party dropped critical systems needed for the space station because the other one had the component. That means physically you can separate the two segments. But if you do it, no one of the two can sustain a long time in space.